November 11th, 2025. Somewhere in a research facility, scientists are staring at their screens, trying to make sense of data that refuses to cooperate with any model they have. The object is called 3I ATLAS. That designation means it's the third confirmed interstellar visitor we've ever detected passing through our solar system. Think about that for a moment. In all of human history, we've only confirmed 3 objects that came from beyond our sun's gravitational influence. 3 visitors from the vast darkness between stars. Atlas just survived perihelion. That's the point in an orbit where an object comes closest to the sun. For a comet, perihelion is brutal. Temperatures spike to over 400 degrees Celsius. Ice that's been frozen solid for billions of years suddenly gets blasted with heat. It doesn't melt, it sublimates, which means it turns directly from solid ice into gas, skipping the liquid phase entirely. Think of dry ice, that solid carbon dioxide that creates fog when you leave it out. Same process, but happening violently, explosively, across an entire object the size of a mountain. Most comets barely survive perihelion. Some break apart completely, torn to pieces by thermal stress and the tidal forces from the sun's gravity. The weaker ones just disintegrate, leaving behind a trail of debris that spreads out along their former orbit. Atlas didn't break apart. Instead, it started doing things that don't match any comet behavior we've catalogued in decades of observations. The brightness didn't gradually increase as it approached the sun, it exploded upward. Gas began erupting from specific points on its surface in patterns that repeated with mechanical precision. Radio telescopes picked up emissions where there should have been nothing but silence, and the trajectory, the path this object is taking through space, shifted in ways that suggest something more complex than simple heating and gas release. Now, as observatories scattered across the planet continue tracking Atlas, the data keeps piling up. And it keeps getting stranger. The main question stopped being, what is this thing a while ago? Now it's become something more unsettling. Are we looking at natural physics we simply haven't encountered before, or are we looking at something that was made? Nobody wants to say that second option out loud. Not in official statements, not in peer-reviewed papers that will be scrutinized by colleagues, not in press releases that the public will read, but in closed-door meetings, in encrypted email threads between researchers who've known each other for years, in conversations happening at 3 a.m. at remote observatories. That question keeps surfacing, because Atlas is not behaving like a comet. It's not even behaving like ʻOumuamua, that first mysterious interstellar visitor that accelerated away from the sun without producing any visible jets of gas or dust. ʻOumuamua was strange enough. Astronomers are still arguing about what it was. Atlas is doing something different, something that when you watch the data accumulate day after day, starts to look less like random natural processes and more like purpose. Let me walk you through what's been happening.
When Atlas was first detected back in April 2024, it looked completely unremarkable. The Asteroid Terrestrial Impact Last Alert System found it. ATLAS, the telescope network, not the object, is a system of robotic telescopes in Hawaii that automatically scan the sky every night, looking for asteroids and comets that might pose a threat to Earth. The telescopes take thousands of images, and software compares each new image to previous ones, flagging anything that moved. On one particular night, the software flagged a new dot, faint, distant, moving slowly against the background stars. Just another dim speck in a sky full of dim specks. Astronomers calculated its trajectory using standard orbital mechanics and immediately realized something important. This wasn't an asteroid from our solar system's main belt. The orbit was hyperbolic with an eccentricity of 6.1. Let me explain what that means. Eccentricity is a number that describes the shape of an orbit. An eccentricity of 0 means a perfect circle. An eccentricity of 0.5 means an ellipse, the stretched oval shape that planets follow around the sun. An eccentricity of exactly 1 means a parabola, an object that's moving just fast enough to escape the sun's gravity, flying away on an open curve that never closes. Anything above 1 is a hyperbola, which means the object is moving way faster than escape velocity. It's not bound to the sun at all. It came from somewhere else, it's passing through our solar system in an almost straight line, and it's going to leave again. never to return. An eccentricity of 6.1 means Atlas is moving through our solar system like a bullet, fast, direct, undeflected by the Sun's gravity. It came from somewhere else. Initial observations using spectroscopy, a technique where you split an object's reflected light into its component wavelengths to see what chemicals are present, showed unusual composition. Very little water vapor, which is strange because most comets are largely water ice, but there were strong signatures of carbon monoxide and carbon dioxide, not just present but dominant, 16 times more abundant than in typical comets from our own solar system. That told researchers Atlas must have formed in extremely cold conditions. We're talking about temperatures close to absolute zero, far colder than anything in our outer solar system, probably in the outermost regions of another star's planetary system, in a zone so distant and frigid that even water ice rarely condensed. Out there, carbon dioxide and carbon monoxide freeze solid, while water remains too sparse to accumulate. Interesting chemistry, sure. Unusual, absolutely. But not alarming. Just another interstellar object with weird composition. Similar to Comet Borisov, the second interstellar object discovered in 2019 by Gennady Borisov, an amateur astronomer from Crimea, who built his own telescope. Borisov had strange chemistry too. Interstellar objects form around different stars with different elemental abundances, so we expect them to look chemically distinct from objects born in our neighborhood. Then came perihelion. October 29th, 2025. Atlas reached its closest approach to the Sun, passing just inside Mercury's orbit at a distance of roughly 44 million kilometers. That's close. At that range, the sunlit side of a comet gets absolutely hammered by solar radiation. Temperatures soar above 400 degrees Celsius. For an object that's been frozen at near absolute zero for billions of years, that's an incomprehensible shock. Ice sublimates rapidly, gas erupts from the surface, and the internal structure, if it's weak, can simply fail. That's when everything changed. The brightness exploded. Within just a few days, Atlas became 5 times brighter than it had been before perihelion. That's not the gradual brightening you see as a comet slowly warms up on its approach to the Sun. That's not the gentle increase in activity astronomers expect as more surface area gets heated and more ice begins to sublimate. That's an eruption, a sudden dramatic outburst. But it wasn't just brightness. When astronomers examined the images, they saw something that made them look twice at their data. Gas jets. Multiple distinct jets of gas erupting from specific locations on Atlas's surface and shooting outward into space. Now, gas jets from comets are normal. As a comet heats up, ice doesn't sublimate evenly across the entire surface. Some areas warm faster than others, because of composition differences or surface topology. Gas escapes more rapidly from those warmer spots, creating visible plumes that stream away from the nucleus. We've observed thousands of comets producing jets. It's textbook behavior. But Atlas's jets were different in a way that made people uncomfortable. They were stable. As Atlas rotates, and we know it completes one full rotation every 9 hours because of periodic variations in brightness, the jets appeared and disappeared in precise patterns. The same jets, in the same positions relative to the object's surface, cycle after cycle. Like watching lighthouse beams sweep across the sky, appearing and vanishing on an exact schedule. Natural jets from comets usually shift and change. As the surface erodes from sublimation, the vents producing the jets widen or collapse. Temperature changes cause the intensity to fluctuate. The direction might drift as surrounding material wears away unevenly. Atlas's jets stayed locked in place. Same positions, same intensity patterns, same timing. Rotation after rotation. And then there was the jet that made people stop and stare at their monitors in silence. One of the jets was pointing directly toward the Sun. Let's talk about some basic physics for a moment,
because this is where ATLAS starts to violate fundamental principles that govern how comets work. When a comet gets close to the Sun, the side facing the Sun heats up. Ice on that sunward-facing surface absorbs solar radiation and sublimates. The gas that forms has to go somewhere, and it escapes outward away from the Sun, for two reasons. First, the pressure of sublimation itself pushes the gas outward from the surface. Think of it like steam escaping from a boiling pot. The gas erupts away from the source of heat.
Second, once that gas is free in space, solar radiation pressure takes over. Photons, particles of light, carry momentum. When billions of photons from the Sun strike gas molecules, they push those molecules away from the Sun. It's a small force on individual molecules, but cumulatively, it's enough to create the characteristic comet tail that always points away from the Sun, regardless of which direction the comet is traveling. This is why comet tails don't stream behind the comet like the trail from a jet plane. They point away from the Sun. If a comet is moving toward the Sun, the tail streams behind it. If the comet is moving away from the Sun after perihelion, the tail points ahead of it. The tail is always being pushed away from the source of radiation. So when gas erupts from a comet's surface, it should move outward, away from the Sun. The direction might be angled due to the comet's rotation or the topology of the surface. But the overall vector should always have a component directed away from the heat source. ATLAS had a jet pointing toward the Sun, not angled slightly inward, not deflected by some surface feature, aimed directly at the Sun, as if something was actively pushing gas in that direction against every natural force that should be opposing it. Scientists immediately started working on models to explain it. In science, when you see something that appears to violate known physics, your first assumption isn't that the physics is wrong. Your first assumption is that you're missing something, that there's a natural explanation you haven't considered yet. Maybe it was random sublimation from a subsurface cavity. Perhaps there was a hollow space beneath the surface where gas accumulated, and when pressure built up enough, it erupted through a crack that just happened to point toward the Sun. Random chance. But random sublimation doesn't produce jets that appear in exactly the same position every 9 hours, rotation after rotation. Random is chaotic, random shifts and changes. Maybe it was structural. Perhaps there was a deep fissure or a channel in the object's interior that directed gas flow in unusual directions, the way a pipe directs water. The geometry of that channel could theoretically aim gas toward the Sun if the internal structure was just right. But channels and fissures erode. Gas rushing through a confined space at high pressure wears away the walls. The channel should widen, the jet should spread out and weaken, the direction should shift as material erodes unevenly. We should see changes over time. ATLAS's sunward jet remained consistent. Maybe it was related to rotation and centrifugal effects. If the object was spinning fast enough, maybe the combination of outgassing and rotational forces could create unusual flow dynamics that bent the jet's path.
But ATLAS rotates every 9 hours. That's actually quite slow for a comet. Centrifugal forces at that rotation rate are minimal, nowhere near strong enough to redirect a gas jet against solar radiation pressure. The model that finally worked, the only model that matched what telescopes were observing, required something very specific. The gas had to be escaping through narrow, confined channels inside the object. Not random cracks, not wide fissures, channels, tubes, passages with consistent geometry that directed the flow of sublimated gas in precise directions. The jets were narrow-band, highly collimated, meaning they stayed focused rather than spreading out into a diffuse cloud. That's exactly what you'd expect from gas flowing through a tube, rather than erupting from an open surface. And here's where the language gets uncomfortable. One researcher, in a private email that later got leaked to an astronomy forum, used a specific word to describe what the observations looked like. Now, let's be completely clear about something. Saying that jets look like nozzles doesn't automatically mean they are engineered nozzles. Natural processes can create structures that resemble engineered devices. Subsurface cavities can form as ice sublimates unevenly beneath the surface. Thermal stress can crack ice and rock in ways that create tunnel-like features. Nature is perfectly capable of producing complex geometry without any intelligence involved. But the precision is what keeps bothering people. The repeatability. Natural channels should show some variation. They should evolve as gas flows through them. They should respond to the chaos of thermal stress and pressure changes. Atlas's jets don't wander. They don't drift. They don't gradually change direction or intensity. They just appear, disappear, appear again, like someone operating a valve on a precise schedule. Self-regulation or hidden mechanics. The behavior of the jets gets even stranger when you look at what happened as Atlas moved away from perihelion. After an object passes its closest point to the Sun, it starts moving outwards again, traveling back toward the outer solar system. Solar heating decreases, temperatures drop, sublimation rates fall, gas production slows down. For most comets, this is a gradual process. Activity doesn't just switch off. It fades over days or weeks as the object cools. Jets sputter and weaken irregularly. Some areas of the surface stop sublimating while others continue. It's messy, chaotic, unpredictable. Atlas's jets shut off one by one, in sequence. Observers tracking the object noticed that as specific regions of the surface cooled below certain temperature thresholds, their associated jets would cease. Not slowly fade, not sputter out with intermittent bursts, just stop, clean cutoffs. One astronomer, speaking off the record, described it as watching someone close a series of doors, one after another, methodically.
Scientists started very cautiously discussing the possibility that Atlas's internal structure might include features that regulate gas flow. Channels that can close when pressure drops below a certain point. Cavities that act as reservoirs, releasing gas only when internal conditions reach specific thresholds. They're extremely careful with their language. Nobody wants to use the word mechanism. Nobody wants to say valve or control system or anything that implies engineering. But the question keeps surfacing in private conversations. Can a natural object behave this precisely? Ice is chaotic. It fractures randomly. It sublimates unevenly. Rock is irregular, full of cracks and weak points that fail unpredictably under stress. Even if channels form naturally through sublimation or thermal cracking, they should erode and change as gas rushes through them. The geometry should be unstable. Yet we're watching Atlas release gas with regularity that looks more like a machine venting pressure than a comet undergoing thermal stress. Controlled releases, repeating patterns, efficient outgassing that follows the object's rotation like clockwork. It's unsettling because it's too clean. Nature is messy. This isn't. October 24th, 2025, 5 days before perihelion, Atlas did something no comet had ever done before in the entire history of radio astronomy. It started broadcasting. Radio telescopes monitoring the object detected sharp, narrow emission lines at two specific frequencies, 1.665 GHz and 1.667 GHz. Those frequencies correspond to hydroxyl radicals, OH molecules, which are fragments of water molecules that have been broken apart by ultraviolet light from the sun. Let me explain how this works. Water is H2O, two hydrogen atoms bonded to one oxygen atom. When UV light from the sun hits a water molecule with enough energy, it can break that molecule apart, creating fragments. One common fragment is hydroxyl, which is just one hydrogen and one oxygen still bonded together. These hydroxyl molecules are unstable and highly reactive, and they emit radio waves at very specific frequencies, 1.665 GHz and 1.667 GHz, as they move through space. Every active comet produces hydroxyl emissions. As ice sublimates and water vapor is exposed to sunlight, some fraction of those water molecules gets broken down, and the resulting hydroxyl molecules emit radio signals at very specific frequencies, 1.665 and 1.667 GHz. Radio astronomers have been detecting these emissions from comets for decades. It's completely normal. But ATLAS's hydroxyl signal was different in ways that made radio astronomers double-check their equipment. First, the timing didn't make sense. The strongest hydroxyl emissions from a comet should occur at perihelion, when solar heating is at maximum intensity and water sublimation is most vigorous. You'd expect the signal to build as the comet approaches the Sun, peak right at perihelion, and then gradually fade as the comet moves away and cools down.
ATLAS's signal appeared 5 days before perihelion. It grew stronger over those 5 days. It peaked exactly at perihelion, and then it continued for exactly 36 hours at consistent intensity before abruptly cutting off. Not fading, not fluctuating, not gradually declining as the object cooled. A clean, stable signal that lasted precisely 36 hours and then stopped like someone flipped a switch. Second, the signal was too narrow. Natural hydroxyl emission from a comet should be broadened by the Doppler effect. Gas molecules erupting from the surface move in all directions at a range of speeds. Some molecules are moving toward Earth, some are moving away, some are moving sideways. Each of those molecules emits radio waves at the hydroxyl frequency. But because they're moving at different velocities, the frequency we detect is shifted slightly by the Doppler effect, the same effect that makes an ambulance siren sound higher pitched as it approaches and lower pitched as it moves away. When you add up all those Doppler shifted emissions from molecules moving in every direction, you get a broad, fuzzy emission line. The signal is spread out over a range of frequencies. ATLAS's hydroxyl lines were sharp, narrowband. The emission was concentrated at very specific frequencies, as if the gas molecules were all moving in a coordinated way, rather than erupting chaotically in all directions. Radio astronomers started using phrases like methodical seepage to describe what they were seeing. One researcher compared it to listening to someone slowly open a valve, hold it at a steady flow rate, then close it again. The 36-hour duration is what really caught people's attention. That's not a random number. ATLAS rotates once every 9 hours. 36 hours is exactly 4 complete rotations, 4 cycles, start to finish, then silence. Could that be coincidence? Sure, natural processes don't care to produce round numbers that humans find meaningful, but the precision keeps raising eyebrows. The signal lasted exactly the length of time it would take ATLAS to complete 4 rotations, then stopped cleanly with no gradual decline. It's another data point that doesn't quite fit the standard model of comet behavior. Individually, you could explain each anomaly. The jets, the radio signal, the brightness surge, each one has potential natural explanations, but together, they're starting to paint a picture of an object that behaves with a level of precision that makes scientists uncomfortable. After perihelion, as observatories continued tracking ATLAS's position against the background stars, orbital mechanics specialists started noticing something wrong. The object wasn't where it was supposed to be. Not dramatically off course, not wildly deviating, just slightly, persistently wrong. The trajectory, calculated from gravitational forces alone, the Sun's gravity pulling on ATLAS, the minor influences from the planets, all the standard factors that determine an object's path through the solar system, predicted one position. ATLAS was in a slightly different position.
And that difference was growing over time. This is called non-gravitational acceleration, and it's not unusual for comets. When gas erupts from one side of a comet, it acts like a tiny rocket engine. The gas carries momentum, and by Newton's third law, every action has an equal and opposite reaction. The comet receives a push in the opposite direction. That push changes the orbit slightly. Astronomers are used to this. They account for it by observing the jets, measuring their intensity and direction, calculating how much force they're producing and adjusting their trajectory predictions accordingly. It's a standard part of tracking active comets. But Atlas's acceleration didn't match its visible jets. The jets were pointing in multiple directions, some toward the Sun, some sideways, some at various angles. If you add up all the forces from all those jets, a vector sum, where you account for both the magnitude and direction of each force, you get a net push in a specific direction. The actual trajectory deviation was in a different direction entirely. And more troubling, the acceleration was constant, not fluctuating with the rotation, not varying as different jets turned on and off with Atlas's 9-hour spin, just a steady, unchanging push that continued day after day. Scientists proposed several explanations, each attempting to reconcile the observations with natural processes. Maybe there were invisible jets on the night side of the object, the hemisphere facing away from both Earth and the Sun. Gas escaping from those hidden regions could produce thrust we couldn't observe directly. That would explain why the net force didn't match the visible jets. But here's the problem. Invisible jets should still vary with rotation. As the object spins, hidden areas rotate into view and visible areas rotate out of sight. The net thrust should change as different jets become visible or hidden. The acceleration should wobble, shift direction, show periodic variations that match the rotation period. Atlas's acceleration was smooth, linear, no periodic variations, no wobbles, just a steady push in one direction.
Maybe there were microfractures distributed across the entire surface, each one releasing tiny amounts of gas too faint to see individually, but collectively producing enough thrust to alter the trajectory. Gas seeping from thousands of small cracks rather than a few large jets. But microfractures release gas in response to heating. As different parts of the surface rotate into sunlight and heat up, those areas should produce more gas. As they rotate into shadow and cool down, gas production should drop. The thrust should pulse, rising and falling with a period that matches the rotation rate. Atlas's thrust was constant, no pulsing, no variation. The acceleration vector, the direction of the push, was locked, steady, unchanging over multiple weeks of continuous observation.
That kind of consistency is extremely difficult to explain with natural outgassing. Gas doesn't push in one direction steadily for weeks. It bursts, fluctuates, responds to changing sunlight and temperature. The fact that Atlas is maintaining a constant acceleration despite rotating every 9 hours, despite moving away from the Sun and cooling down, despite all the factors that should cause variations, that's what's making orbital mechanics specialists nervous. Because there is something that pushes steadily in one direction for weeks, maintaining a constant acceleration regardless of external conditions. An engine. Nobody's saying that in official papers. Nobody wants to be the one who goes on record suggesting Atlas has propulsion. But it's there, hanging unspoken in every technical discussion about the trajectory anomaly. This is starting to remind people of ʻOumuamua. That first interstellar visitor accelerated too, in ways that didn't match any visible gas emissions. Researchers proposed all sorts of exotic explanations. Maybe it was being pushed by sunlight reflecting off an extremely thin, light structure, essentially a solar sail. Maybe it had bizarre surface properties that created asymmetric thermal radiation, producing thrust through photon emission. But with Atlas, we're seeing the same pattern again, an interstellar object that doesn't obey the standard rules, an object whose trajectory suggests forces we can't directly observe, an object that moves like it has intention. Before perihelion, spectroscopic observations showed Atlas reflecting light in a way consistent with organic rich material. The spectrum had a reddish tint, similar to what we see in many outer solar system objects and interstellar comets.
Red coloration in space objects usually indicates the presence of carbon-based compounds, organic molecules that have been broken down and altered by radiation over long timescales. When cosmic rays, high-energy particles flying through space at nearly the speed of light, strike organic molecules, they break chemical bonds and create new compounds. Over millions or billions of years, this radiation processing creates a characteristic reddish color. Red objects are typically old. The reddish tint is essentially a patina of age, evidence that the material has been exposed to the harsh environment of space for a very long time. Then, Atlas passed through perihelion. When it emerged on the other side, when telescopes got a clear view of it again, after weeks of being too close to the sun's glare for safe observation, something fundamental had changed. The color was different. Not slightly different, not a subtle shift in the spectrum that required careful analysis to detect, dramatically, obviously different. In the span of just a few days, maybe even hours, though we couldn't observe continuously during closest approach, Atlas shifted from reddish-brown to deep metallic blue. That's not normal.
Color changes in comets do happen. As ice on the surface sublimates away, it exposes deeper layers. If the interior has a different composition than the exterior, you'll see the object's color shift as fresh material becomes visible. We've observed this with comets from our own solar system. But red to blue? That's extreme. That's not just exposing a deeper layer of slightly different ice, that's revealing something fundamentally different beneath the surface. Blue coloration in astronomical spectroscopy typically indicates one of two things. Either you're looking at clean, fresh water ice, frozen water that hasn't been exposed to radiation, which reflects blue wavelengths preferentially, or you're looking at metal. Detailed spectroscopic analysis of post-perihelion Atlas showed something that made astronomers sit up in their chairs and start checking their instruments for errors. Strong absorption lines consistent with nickel. Not trace amounts, not minor contamination that might be present in any rocky object, substantial nickel content enough to dominate the reflectance spectrum and give the object that distinctive metallic blue appearance. Nickel is a metal found in asteroids, particularly in a specific type called iron meteorites. These are fragments from the cores of differentiated bodies, objects that were once large enough and hot enough to separate into layers, with heavy metals like iron and nickel sinking to the center and lighter rocky material floating to form a mantle and crust. When these bodies are destroyed through collisions, fragments of the core can survive as iron-nickel meteorites. Finding nickel in an asteroid fragment isn't unusual, but comets aren't supposed to have metal cores. Comets form in the outer solar system where temperatures are extremely cold. They're made of ice, dust and rocky material all loosely packed together in a fragile structure. They're dirty snowballs in the classic description. There's no heat, no pressure, no mechanism to create a differentiated interior with a metal core. Yet Atlas, after perihelion, looks like it has a metal core. Or more precisely, it looks like it is a metal core, with the outer layers of ice and dust stripped away by solar heating. The reflectance patterns are unusual too. The way sunlight bounces off Atlas's surface now doesn't match rough, irregular rock. It matches smooth metal. High reflectivity with specular reflection, light bouncing off at consistent angles rather than scattering diffusely the way it does from a dusty, irregular surface. One researcher, speaking anonymously to avoid professional backlash, described the post-perihelion surface as almost machined. That word keeps appearing in informal discussions: machined, processed, refined, terms that imply artificial modification rather than natural processes. Nobody is publishing these observations in that language. The official papers carefully describe anomalous reflectance properties and unexpectedly high metal content. But in private, researchers are looking at the data and seeing something that resembles manufactured metal more than natural rock.
Here's where the story takes a frustrating turn for anyone trying to understand what's actually happening with ATLAS. NASA's Mars Reconnaissance Orbiter, MRO, a spacecraft that's been circling Mars since 2006, equipped with high-resolution cameras designed to map the Martian surface in extraordinary detail, had a unique opportunity to observe ATLAS during its perihelion passage. From Mars's position in its orbit at that time, MRO had a clear, unobstructed view of ATLAS that wasn't hindered by the sun's glare the way Earth-based observations were. During perihelion, when ATLAS was at its most active and most interesting, observers on Earth couldn't point their telescopes at it because it was too close to the sun. Looking at something near the sun risks damaging sensitive instruments with scattered light and direct solar radiation. But MRO, from its vantage point at Mars, could observe safely. And it did. MRO's cameras were directed at ATLAS. Multiple images were captured over several days, documenting the object at its closest approach to the sun during the peak of the brightness surge while the jets were at maximum intensity. Those images should have been released to the public within days. That's NASA's standard procedure. Data from publicly funded missions is supposed to be made available as quickly as possible so that researchers worldwide can analyze it. The images weren't released. Days passed, then a week, then 2 weeks. Astronomy forums started filling with questions. Where are the MRO images? Why the delay? What did MRO see that requires this much processing time? NASA remained silent. 3 weeks after the observation, the images were finally released, and when researchers opened the files, the reaction was largely disappointment mixed with suspicion. The images were heavily compressed, much lower resolution than MRO's cameras are capable of producing, cropped to show only a small region immediately around ATLAS with no surrounding context or background stars that would allow for independent verification of the object's position and appearance. And, critically, no raw data. Raw data is the unprocessed, uncompressed information directly from a spacecraft's instruments. It's what scientists actually want because it lets them apply their own processing techniques, examine details that automated systems might miss, and verify that the released images haven't been altered or selectively edited. NASA released only processed images, compressed, cleaned, adjusted for contrast and brightness, ready for public viewing, but stripped of the detailed information that researchers need. The official explanation appeared in a footnote on the data release page. Images require contextual analysis before publication. That's unusual phrasing. NASA typically releases data as quickly as possible, sometimes within hours of receiving it from a spacecraft. Delays do happen. Bandwidth constraints, storage issues, software problems, but those are technical delays, not analytical ones.
Contextual analysis suggests something different. It suggests that someone examined the raw images and determined they needed interpretation before being shown to the public. It implies that the images contain something that requires explanation, something that shouldn't be released without proper framing. Congress noticed. Members of the House Committee on Science, Space and Technology, the congressional committee responsible for oversight of NASA and other science agencies, sent a formal letter to NASA's administrator demanding immediate release of all data related to ATLAS. Not just the processed images, but the raw files, telemetry data, and any internal analysis documents that explained the delay. The letter was polite but firm, invoking the principle that data collected by publicly funded missions belongs to the public. Delays in releasing information about an object of extraordinary scientific interest raise questions about transparency and accountability. NASA responded with a carefully worded statement about data validation procedures. They emphasized the need to ensure accuracy before publication, to avoid releasing information that might be misinterpreted or contain artifacts from instrumental errors. They promised full data release pending completion of standard review protocols. That response was issued 2 weeks ago. The raw data still hasn't been released, and NASA hasn't provided a timeline for when it will be. Meanwhile, something strange started happening on astronomy forums and social media platforms where researchers share information. Leaks. Someone with access to NASA systems, or claiming to have access, started posting image fragments, pieces of data, screenshots that appeared to show Atlas at much higher resolution than the official release. The leaked images are impossible to verify. They could be elaborate fakes, digitally manipulated to look like genuine spacecraft data. They could be misinterpreted legitimate data, artifacts from image processing that resemble features but aren't real. Or they could be authentic images that someone inside NASA decided the public should see. What the leaked images appear to show is an object that doesn't look like any comet we've ever observed. The shape isn't rounded or irregular like a natural body. It's angular, geometric. There are straight edges visible, lines that don't waver or curve the way natural erosion patterns do. Shadow patterns that suggest the surface isn't rough and cratered, but composed of distinct planes meeting at sharp angles. One leaked image shows what appears to be a regular pattern of surface features, evenly spaced in a grid-like arrangement. Natural cratering is random. Natural fracturing creates irregular patterns. This looks organized. Are these leaks real? There's no way to know without access to the original raw data. Image forensics experts have examined the leaked files and found no obvious signs of digital manipulation, but modern photo editing tools are sophisticated enough that absence of detected manipulation doesn't prove authenticity.
What we're left with is uncertainty, official images that don't show much, promises of full data release that keep getting delayed, leaked images that show something extraordinary but can't be verified, and a growing sense among people following this story that something about NASA's handling of Atlas observations doesn't add up. Let's talk about how old Atlas is, because this detail adds a profound layer of strangeness to everything else we've discussed. When astronomers analyze the light reflected from an object in space, they're doing more than just looking at brightness and color. They're examining specific wavelength where particular atoms and molecules absorb light, leaving dark lines in the spectrum called absorption lines. These lines are like fingerprints, unique identifiers that tell you exactly what chemicals are present. But there's more information hidden in those spectral lines. The precise position and shape of each line depends on isotopic composition. Isotopes are variants of the same element with different numbers of neutrons in their nuclei. For example, oxygen comes in 3 stable isotopes: oxygen-16 with 8 protons and 8 neutrons, oxygen-17 with 8 protons and 9 neutrons, and oxygen-18 with 8 protons and 10 neutrons. They're all oxygen, they all behave the same way chemically, but the ratio between these isotopes, how much of each variant is present, depends on where and when the material formed. Our solar system has a specific isotopic signature. When the molecular cloud that would become our sun and planets collapsed about 4.6 billion years ago, it had a particular mix of isotopes inherited from previous generations of stars. Every object born in our solar system carries that signature. It's a fingerprint that says, I formed here, in this stellar neighborhood, from this particular cloud of gas and dust. Atlas doesn't have that signature. Detailed spectroscopic analysis shows isotopic ratios that are significantly different from anything in our solar system. The ratios suggest formation in a stellar environment with a different chemical history than our own. And more importantly, the patterns are consistent with material that's extremely old. Current estimates based on isotopic analysis put Atlas's formation age at over 7 billion years. Think about that for a moment. Earth formed 4.5 billion years ago. The Sun ignited 4.6 billion years ago. Our entire solar system is roughly 4.6 billion years old. Atlas is older than all of that. It existed before our Sun was born. It was already ancient when the cloud that would become our solar system was still just diffuse gas drifting through the galaxy. 7 billion years ago, the universe itself was less than half its current age. The Milky Way galaxy looked completely different. There were fewer heavy elements, carbon, oxygen, iron, nickel, because fewer generations of stars had lived and died to create them. The stellar populations were different. The structure of the galaxy was still forming through mergers and collisions with smaller galaxies.
Atlas is a relic from that ancient era, a fragment from the early galaxy, from a time when conditions were vastly different than today. Where did it come from? One possibility, it's a fragment from a destroyed planet. Not a planet in our solar system, obviously, but one that orbited a star that no longer exists. That star formed, lived its life, exhausted its fuel, and died. Depending on its mass, it might have ended in a supernova, a catastrophic explosion that destroys the star and scatters everything orbiting it. Or it might have ended more quietly, swelling into a red giant that engulfed its inner planets and ejected its outer layers into space, leaving behind a cooling white dwarf. Either way, the planetary system around that star was destroyed. Everything was scattered into interstellar space. Most of it would have been vaporized or blown into tiny particles. But the densest, most massive fragments, particularly pieces of a planet's core, might have survived intact. If Atlas is a fragment of a planetary core, that would explain the nickel content. Planetary cores are composed primarily of iron and nickel, compressed under enormous pressure during the planet's formation. When a planet is destroyed, the core can break into chunks that get ejected into space with enough velocity to escape the dead star's gravity. Those fragments would wander the galaxy for billions of years, slowly accumulating a coating of ice and dust as they drifted through molecular clouds and cold interstellar regions. Over time, they'd stop looking like metal cores and start looking like ordinary comets or asteroids buried under layers of frozen volatiles and organic material, until they passed close to a star again. Then solar heating would strip away those outer layers, revealing the metal underneath.
That's a plausible, natural explanation for what we're seeing, an ancient planetary core fragment wandering space for billions of years, temporarily unmasked by perihelion. But there's another possibility, one that people discuss very carefully, usually late at night in private conversations, away from colleagues who might think they've gone too far into speculation. What if Atlas isn't entirely natural? 7 billion years ago, the universe was younger, but it was still old enough for complex chemistry. Stars had been forming and dying for billions of years already. Heavy elements existed. Planets existed, and if life emerged on some of those planets, if intelligence developed, if civilizations rose to the point where they could build things designed to travel between stars, what would a 7 billion-year-old artifact look like? It would be ancient beyond comprehension, battered by cosmic radiation for eons, coated in layers of ice and dust accumulated from drifting through countless molecular clouds. Any surface features would be eroded, buried, unrecognizable.
Inside, if anything remained functional, it would be systems designed for extreme longevity. No moving parts that could wear out, no complex electronics that could fail, just the most basic, robust mechanisms. Maybe nothing more than passive systems that respond to environmental triggers, heat, light, gravity. And if such an object passed close to a star after billions of years in cold storage, if solar heating stripped away the accumulated debris on its surface, you might see structure again. Briefly. Metal that's too pure to be natural. Geometry that's too regular to be random. Behavior that's too precise to be chaotic. Then the object would move away, cool down, and fade back into the darkness. Maybe never to be heated again. Maybe to wander for another billion years before encountering another star. This is speculation. There's no proof. But the question keeps surfacing.
Can we completely rule it out? There's a coincidence that keeps getting mentioned in discussions about Atlas, and while it might be pure chance, it's strange enough that it deserves attention. On August 15, 1977, a radio telescope in Ohio detected something extraordinary. The Big Ear telescope was part of SETI, the Search for Extraterrestrial Intelligence, a project that systematically scans the sky looking for narrow-band radio signals that might indicate artificial transmissions from other civilizations. The astronomer reviewing the data was Jerry Amon, a volunteer researcher who was checking computer printouts from the previous night's observations. At 11:16 p.m. on August 15th, the telescope had detected an extremely strong, narrow-band signal at 1,420 megahertz. That frequency is significant. It's the emission line of neutral hydrogen, the single proton and single electron that make up the simplest, most abundant atom in the universe. It's a frequency that any technologically advanced civilization would know about because hydrogen is everywhere. It's also in a relatively quiet part of the radio spectrum where natural cosmic noise is low. In SETI research, 1,420 megahertz is considered one of the most logical frequencies to use for interstellar communication. If someone wanted to send a signal that other civilizations would notice, they'd probably use the hydrogen line, because everyone would be listening there. The signal Jerry Amon saw was so strong, so clearly narrow-band and artificial-looking, that when he spotted it on the printout the next day, he grabbed a red pen, circled it, and wrote "Wow" in the margin. The wow signal. It lasted exactly 72 seconds. The precise amount of time the telescope's beam was pointed at that region of sky as Earth's rotation swept the antenna across the heavens. After 72 seconds, the signal was gone. The telescope had rotated past the source. The signal came from the direction of the constellation Sagittarius, from a region of space with no known bright stars, no obvious source.
And it never repeated. Despite decades of searching, despite pointing more sensitive telescopes at that same region hundreds of times, the signal has never been detected again. It remains one of the most intriguing, unsolved mysteries in SETI history. Now here's the strange part. Atlas's trajectory traces back to almost the same region of sky. Not exactly the same. There's a difference of about 9 degrees, which sounds close but represents an enormous distance in space, but it's close enough that people have noticed. And Atlas's radio emissions are at 1.665 and 1.667 megahertz, the hydroxyl lines. Hydrogen at 1420 megahertz, hydroxyl at 1665 and 1667 megahertz. Together, those frequencies bracket what SETI researchers call the water hole, the range of radio spectrum between the hydrogen line and the hydroxyl lines where natural cosmic noise is at its minimum. It's called the water hole because hydrogen and hydroxyl are the components of water. H plus OH equals H2O. The water hole is considered the most promising part of the spectrum to search for artificial signals because any advanced civilization would recognize it as a natural place to look. The frequencies are significant because of their connection to water, which is essential for life as we understand it. The noise is low, making signals easier to detect. It's the cosmic equivalent of a designated meeting point. The WOW signal came from Sagittarius at the hydrogen line in 1977. Atlas is arriving from near Sagittarius with hydroxyl emissions in 2025. Is this meaningful? It's impossible to say. The galaxy is vast. Objects approach from all directions. 9 degrees of separation on the sky could represent trillions of kilometers in actual space. The connection could be pure coincidence. But it's worth noting that both events share several characteristics. They're rare. They're one-time occurrences with no repetition. They involve frequencies directly related to water, and they originate from the same general direction in space. Some researchers have quietly suggested that if someone or something was attempting to mark objects or signals for attention, using the water hole frequencies would be a logical choice. It's a beacon strategy that says this is worth noticing in a language that any civilization capable of radio astronomy would understand. It's speculation without proof, but the coincidence is there, documented, and undeniable. Atlas has systematically violated nearly every expectation we had about interstellar comets. It brightened too suddenly after perihelion. The surge was too sharp, too dramatic for normal sublimation processes. Its jets are too stable and precise. Natural gas eruptions shouldn't maintain fixed positions and consistent intensity across multiple rotation cycles. They should shift, change, evolve as the surface erodes. One jet points toward the sun, violating basic physics about how gas should behave in the presence of solar radiation pressure.
The radio signal was too clean and too precisely timed. Natural hydroxyl emissions should be broad and chaotic, not narrowband signals that last exactly 4 rotation periods before cutting off. The non-gravitational acceleration doesn't match the visible jets. The trajectory is being altered by forces we can't directly observe, and the acceleration is too constant, too linear to match the fluctuating outgassing we'd expect from thermal processes. The color change from red to metallic blue revealed substantial nickel content. Comets aren't supposed to have metal cores. The isotopic analysis indicates an age of over 7 billion years, making ATLAS older than our entire solar system and a relic from the early galaxy. And NASA is being unusually secretive about observations from their best cameras, delaying data release and providing only heavily processed low-resolution images. So what is ATLAS? There are fundamentally 2 possibilities, and both are profound in different ways. First possibility, ATLAS represents natural processes we simply don't understand yet. Maybe objects that have been wandering interstellar space for billions of years develop internal structures we've never seen before. Maybe the interaction between ancient metal-rich cores and accumulated volatiles creates regulatory features that look artificial but aren't. Maybe cosmic ray bombardment over eons creates channels and cavities that direct gas flow with unexpected precision. Our understanding of comets is based on objects from our own solar system. We've studied hundreds of them, but they're all relatively young, born 4.6 billion years ago when our solar system formed, and they've all spent their lives in the sun's neighborhood. We've never had the opportunity to study something like ATLAS, 7 billion years old, that formed around a different star in a different part of the galaxy and has been traveling through interstellar space, experiencing conditions we can only guess at. Maybe we're just seeing natural phenomena we've never encountered because we've never had access to this type of object before. New physics, new chemistry, the universe revealing that it's far more complex and diverse than our limited experience suggested. That's the conservative interpretation, the scientifically safe position, and it might be entirely correct. Nature is capable of producing extraordinary complexity without any intelligence involved. Intricate patterns in snowflakes, fractals in coastlines, self-organizing systems in weather patterns. The universe doesn't need engineers to create structure, but there's a second possibility, one that scientists discuss quietly and carefully, usually with heavy disclaimers about speculation and the need for more data. What if ATLAS carries evidence of engineering? Not recent engineering, not a probe sent by some current galactic civilization, but ancient technology, built 7 billion years ago, when the universe was young and the Milky Way looked completely different than it does today. Maybe some civilization reached the point where they could build objects designed to survive for billions of years, designed to travel between stars, designed to do something. We don't know what. We can't know what. We can barely imagine what a civilization that existed 7 billion years ago might have wanted or needed. Maybe it was exploration. Maybe they sent probes to other stellar systems to gather data, to search for life, to map the galaxy. Maybe ATLAS was one of those probes, launched into the darkness billions of years ago with instructions to visit stars, observe, record, and continue traveling. Maybe it was communication. Maybe ancient civilizations used physical objects as messages, knowing that radio signals would fade and disperse over interstellar distances, but that carefully designed artifacts could survive indefinitely. ATLAS could be a message in a bottle, thrown into the cosmic ocean billions of years ago, finally washing up on our shore. Maybe it was preservation. Maybe a dying civilization, knowing their star was approaching the end of its life, built objects designed to carry information or technology forward in time, seeds of their existence cast into space in hope that someone, someday, would find them and know they existed. We don't have proof of any of this.
We don't have clear images showing manufactured structures. We don't have samples we can analyze in laboratories. We don't have the smoking gun that would definitively prove artificial origin. But we can't completely rule it out either. And that uncertainty is significant, because it represents a fundamental limitation in our current understanding and capabilities. Here's what we do know for certain. ATLAS is behaving in ways that don't match our models of natural comets. The precision of the jets, the timing of the radio signal, the constancy of the acceleration, the revelation of a metal-rich core. Individually, each anomaly might have a natural explanation. Together, they paint a picture of an object that seems to operate according to rules we don't fully understand. Whether those rules are natural laws we haven't discovered yet, or principles of engineering implemented billions of years ago, the result is the same. We're confronted with something that challenges our assumptions about what's possible. Regardless of what ATLAS actually is, its passage through our solar system has revealed something crucial about the limits of our knowledge. We built our understanding of comets and asteroids based on the objects immediately around us. We studied thousands of them, developed detailed models of their composition and behavior, and assumed those models would apply to any similar object we might encounter.
ATLAS has shown us that assumption was premature. The universe is not obligated to conform to patterns we've observed in our tiny corner of space. Objects exist out there, billions of them, wandering the darkness between stars, that were born in environments radically different from our own, that have experienced conditions we've never imagined, that carry within them the chemical and physical signatures of stellar systems that died before our sun existed. Some of those objects will look strange to us, some will behave in ways we can't immediately explain, and some might not be entirely natural. That last possibility is what makes ATLAS so important, not because we have proof of artificial origin, but because we can't definitively rule it out. The data is ambiguous enough that both natural and artificial explanations remain plausible. That ambiguity should drive us to do better. We need better telescopes with higher resolution. We need spacecraft capable of intercepting and studying interstellar visitors up close. We need more sensitive instruments that can detect subtle details our current equipment misses. We need transparent data policies that ensure observations are released quickly and completely so that researchers worldwide can analyze them. The secrecy around the MRO observations is frustrating precisely because ATLAS is too important to keep quiet about. If the images show something extraordinary, we need to know. If they show nothing unusual and the delay is just bureaucratic inefficiency, we still need to know because public trust depends on transparency. ATLAS started as a dim dot moving against the stars, just another interstellar visitor, catalogued and tracked according to standard procedures. Now it's become a test case for how seriously we take the possibility that not everything moving through space is just a rock. Some objects carry history written in their isotopic ratios. Some carry chemistry from stellar forges that no longer exist. Some carry the scars of planetary destruction, fragments of worlds that died billions of years ago. And some perhaps carry evidence of minds that existed long before Earth formed, civilizations that rose and fell and vanished while our sun was still just a slight condensation in a molecular cloud. Builders who created things designed to outlast everything, to travel between stars, to survive until someone noticed them. We don't know if ATLAS is one of those objects. We might never know for certain. The data might remain forever ambiguous, open to multiple interpretations that we can't definitively choose between. But the fact that we're asking the question, seriously, in technical papers and congressional hearings, with orbital data and spectroscopic analysis to back it up, represents progress. We're acknowledging that the universe is stranger and older and more diverse than we thought. We're accepting that our models are incomplete.
ATLAS is still out there, moving away from the sun, cooling down, fading back toward the darkness. Observatories continue tracking it, watching for any additional anomalies. Radio telescopes listen for more signals. Researchers calculate and recalculate its trajectory, trying to determine where it came from and where it's going. NASA still hasn't released the raw MRO images. Congress is still asking questions. And somewhere, teams of scientists are looking at data they can't fully explain, wondering whether they're about to discover new physics or something far more extraordinary. We're living through a moment of genuine uncertainty. An object 7 billion years old has passed through our solar system, exhibiting behavior that challenges our understanding. That's not speculation or conspiracy theory. That's documented, measured, verified fact. What we do with that fact, how we interpret it, what questions we ask next, what resources we dedicate to finding answers, will define how seriously we take the possibility that we're not the first intelligence to look up at the stars and wonder what's out there. Because the universe is vast and ancient and full of things that don't owe us explanations. Atlas reminded us of that. It showed us an object that doesn't fit our categories, that behaves according to rules we're still trying to understand, that carries within it evidence of stellar systems and timescales that make our entire civilization feel like a brief moment. And it's still moving, still out there, still carrying whatever secrets it holds deeper into space, away from our telescopes and our questions. Maybe we'll figure it out eventually. Maybe future observations will reveal a natural explanation that makes everything click into place. Maybe we'll look back and laugh at how we briefly entertained the possibility of artificial origin. Or maybe we'll look back at this moment as the time when we first encountered evidence of something built by minds that existed billions of years before us. The first artifact, the first proof that intelligence isn't unique to Earth, that civilizations have risen and fallen throughout the galaxy's history, that some of them left traces that can survive across unimaginable gulfs of time and space. We don't know yet. The data is still coming in. The analysis continues. The debate goes on. But Atlas happened. It's real. And it's changed what we think is possible out there in the dark.